Hey guys, I just wanted to come in and give you one last important bit of information about solving these homogeneous linear systems of differential equations. And that is something called the phase portraits for them. So this is actually a visual understanding of what the solutions that we've been finding really mean. We're going to draw some pictures. Okay, and I want you to be able to tell me what kind of picture you would get for a particular linear system. I'm only going to talk about this for 2x2 linear systems, so you don't really have to worry too much about it for larger systems. And it's really just a nice little add-on to what we've already learned. We've done all the algebra, all the procedure to come up with the general solution to these kind of problems, but there's an interpretation of them visually that I think is worth just a few minutes to kind of explain to you. Okay? You may recognize the example that I've put on the board here. We did it in class, and it was the very first example really where I solved a linear system for you. Here was my 2x2 matrix, okay? And we found the eigenvalues, which were 5 and -3. It's a non-defective matrix, right? And the corresponding eigenvectors, we worked those out by looking at the null spaces. And we got these two vectors here. From there, we were able to put together the two basic solutions here. Here's the first one, the x1 right here, and the x2 right here. And from that, we could then write down the general solution to the system. So that's what's in the box over here on the right. Okay? I want to talk about how we can draw these solutions and understand what they really mean. Okay? The first thing to remember is that every general solution really has infinitely many solutions within it, right? Because you can choose the numbers C1 and C2 any way that you like, okay? So there's actually infinitely many solutions, and I'm going to draw them on this x1, x2 plane, and what I'm going to be drawing is called a phase portrait for the linear system, okay? To come up with the phase portrait, what you need to do is draw some specific solutions here. And the ones that I'm going to focus on, I'm going to go ahead and we have all this stuff already figured out, so I'm going to erase this and just keep track of my general solution over here. Okay, so we need this part right here. Okay, I am going to choose various values of C1 and C2, specific numbers that will give me specific solutions within this general solution. So for example, I could let C1 equal 1 and let C2 equal 0, right? Now, if I did that, let's look at what we would have over here. Well, what we would have if C1 is equal to 1 and C2 is equal to 0 is we would have this solution right here. Okay? Now, this is a solution that changes with time, right? So for example, at time 0, x of 0 is -1, 1. I'm going to go ahead and draw that on my graph right here. Okay? And then as time increases, as time goes forward, this exponential just gets bigger and bigger, right? But the direction of the vector is still going to be along the same direction as the vector -1, 1. It's just going to be stretched. Right? This is like stretching this vector. As time goes on, what's going to happen is this vector is just going to go out away from the origin. Imagine that you drop a feather into this x1, x2 plane, and you just watch what happens as time goes on. So at time 0, the feather sits right here, and there's either airflow or water flow, whatever it is, this feather basically is going to float somewhere in this plane. And the fact of the matter is, as t gets bigger, the feather is going to just follow the vector -1, 1 out towards infinity, right? We could also run time backwards. We could actually let t go back towards negative infinity. And what we would see if we sort of rewind the tape to negative values of t is that this feather would actually eventually, as t goes towards minus infinity, well, this feather would have started at the origin. Okay? So this straight line is actually a curve that comes to life as a function of t. As time changes, the position along the curve changes. It's kind of just like parametric equations that you would have learned about in calculus. All right? So this is one solution. This is the solution that corresponds to C1 equals 1 and C2 equals 0. Now, what if I let C1 equal negative 1 and C2 equals 0? Well, if I do that, I'm going to get a different solution now, right? So maybe I should, just over here, I'm just going to write down, this is x of t equals e to the 5t times negative 1, 1. If I change C1 to negative 1, I'm just going to negate that vector. And that just means that my solution now is going to go exactly in the opposite direction, right? This curve going in the opposite direction here, this is the solution negative e to the 5t times negative 1, 1. Okay, so it would look just like that. All right? So there's your second solution. Okay? Another good curve to examine would be the curve where C1 is 0 and C2 is 1. Okay, now this time what's going to happen is if C1 is 0 and C2 is equal to 1, we're going to get e to the negative 3t times 7, 1. At time 0, this particle is going to be over here at 7, 1, which is going to be right about there. Okay? That's at time 0. If I put 0 in for t, the exponential part just is e to the 0, which is 1. So I just get the vector 7, 1. Now as time moves forward, that 7, 1 is going to get multiplied by something that's going towards 0. So actually the feather, if you drop the feather in from there, is going to go towards the origin. Right? It's going to actually approach the origin at that point. So this is the solution. X of t equals e to the negative 3t times 7, 1. And if we go in the opposite direction, well, if we take C1 equal to 0 and C2 equal to negative 1, we're basically going to, again, get the mirror image of the first solution, and this time the arrows are going to go in the opposite direction towards the origin. Okay, so in other words, if I put a minus sign in here, right, then starting at negative 7, negative 1, this particle is going to start approaching towards the origin. Okay? Now, there's lots of other choices of C1 and C2. I could start right here, for example. This could be my initial condition, and so x of 0 is equal to that point. In that case, the C1 and the C2 might both be non-zero numbers, right? Which would mean you have kind of a combination of the two vectors here. But what's going to happen in this case, if you drop your feather in right here, it's going to kind of try to line up with the arrows that I've already drawn on the phase portrait. So it's going to do something kind of like this. It's going to be curved. It's not going to be the straight lines, the big X that we have here out of the two basic solutions that we've already looked at. These solutions are going to be curved, but they're going to kind of follow the same direction as the arrows that you see. So what I like to do when I'm drawing these phase portraits is just show a few of these curves to kind of get the idea of what it kind of looks like. Okay? This is actually what is called a saddle. The nature of this particular phase portrait, the origin looks like a saddle. It's like, you know, if you step off of the saddle in one direction, you go out to infinity forever. And if you step off the saddle along another direction, you get sucked into the origin, right? So it's a saddle. The main reason that it's a saddle is because one of the eigenvalues was positive and one of them was negative. See, this e to the 5t blows up to infinity, whereas the e to the negative 3t shrinks to the origin as time goes on. So as time gets bigger, the exponential one, which is the one that's the positive exponential one, is diverging from the origin, whereas the negative exponential term is collapsing towards the origin. Okay, so the signs of the eigenvalues are opposite. One of them is positive, one of them is negative. We're going to get a saddle. Now, you can probably imagine that if we